All right, so today is going to be purely paper exercise, but the looping variance precondition, postcondition, we kind of present them using assertions in Java. There is a way to actually check these assertions at runtime. Just for your information, I'm going to maybe include some brief instruction, or I can briefly mention that on Monday's class. Okay, but usually you can assume whenever you're given like a looping variant question there, you will have to know how to put them in the form that we're going to talk about today, especially universal quantification or existential quantification. It's actually quite normal. You have to use those syntax. I think I also organized maybe some background slides, very brief, for you to also brush up about the necessary bits for predicate logic. That's also going to help on the exam. Okay. All right, so let's now, okay, just before that, so in case you haven't, under the graph lecture notes over here, you can see week number 10. That's where we are. If you click on the first link, it's going to be the instruction of the exercise we're going to look at today. You can feel free to read it through, but I'm going to mainly just focus on my iPad notes today. I also got a screenshot of everything. All right, so I'm going to go from there. And also another document here would be the iPad notes I'm using today. You can also download it. Okay, so along the way. Okay. Right, so this question here is a very typical iterative algorithm. Of course, when we talk about looping variance, it's only for iterative algorithm. For any recursive algorithm, we don't really talk about that in this course, so you don't really have to worry about. So I wouldn't give you some recursive algorithm and ask for looping variance. It's not possible, right? So let's look at this one here, right? It's a very typical one. I'm pretty sure this one you solve it back in the first year, but let's just take a look, okay? So this, let me highlight in gray the algorithm part, and then we'll talk about how we can add like a precondition, postcondition looping variant gradually, okay? We're going to experiment a little bit today, okay? So this is the header of the method. I just write it in Java, right? We have some initialization, okay? So we basically have two local variables. We got I, some loop counter, and also the result. Eventually, we're going to return it. And also, number 3, we also got some input parameter, like an input integer array. Okay. And then we also have a while loop right here. Somehow, I put the state condition here a little bit not as the standard way. I think in the standard way, you would have written like I strictly less than a.length. I'm pretty sure that most of us will write it. But somehow to really make the correctness proof a little bit easier and more straightforward, I put it in a slightly different way. But it will still work. Okay. And then I got if conditional, right? And then I got this one here and also this one here. That's the last line. Okay. And then, of course, that's closing the while loop. And finally, we got return. Okay. Of course, conceptually, it doesn't really matter if you put assert postcondition here or here, but to really make it more sensible programmatically, you should really check it before you return, right? So that's why I put as a very last statements, very last, like pretty much the last line, unless you have a return, okay, for postcondition. Right, so this algorithm here, we don't really have to remind you very much, but let's say we have some input array. Okay, so let's say the input array we consider, let's say 20, 10, 40, and 30, right? Of course, we're going to do a linear scan. That's why it's a linear iterative algorithm. And then the index is going to start from 0, and the very first result is going to be A at index 0. So you can think about this part here, if you kind of recall what we annotated back in the lecture. Think about this part here is about the initialization. The purpose is really to make sure this part here can establish the looping variant for the very first time, before the very first iteration. So this is the S init that we talk about in the slides, right? So now we do have something, right? S init, initialization. And then this part over here will be the body of the loop right here, okay? Basically, except for the very last line, which is about preserving the looping variance. So this is the S, the body of the loop, all right? So now you see more example about how they can look like, okay? All right. And how it works? Well, very straightforward. You basically keep the result updated whenever necessary. So if the current one, for example, result from after the first iteration should be 20. in the second iteration, result doesn't need to be updated. As soon as we get to the third one, because the current element, 40, is larger than the current result, which is 20, we're going to update it, etc. It's a very simple algorithm that we learn. All right? In some way, you can think about the result. I want to draw some analogy. You want to think about, they're really doing the same thing. How can this be somehow related to the Dijkstra algorithm? All right? You want to think about the result here. Okay, some analogy right here. Okay, the result. Think about the result is the temporary computed results so far. Or in this case, of course, maximum, right? So if you think about the Dijkstra, you may actually want to say it's a little bit similar to the capital D value, right? Of course, right? The capital D value. D value. Because we know that D will somehow be finalized at some point, okay? But here, the maximum can only be finalized after the whole iteration, right? I mean, after the whole while loop has been terminated. Another thing I want you to also think about, right? The index I, which is another local variable, it kind of tells us where we are. For example, I could be here, I could be here, and I could be here. So we are basically going from the left to right, where we are trying to cover more and more area in the array, right? So more and more area. It's a little bit like a capital S set that we set for the Dijkstra. Okay. So the I here is really somehow 0 all the way to about I. Specify the area of array already considered. Okay, that's also very important. So you can think about this one here is a bit like the capital S in Dijkstra's algorithm. Okay, just draw some analogy. And I would say many iterative algorithms will follow a similar pattern, right? So that's why we kind of talk about loop invariant only in the Dijkstra algorithm, and now we just do another example. Okay. So let's start with something more like a global. You can think about loop invariant in some ways more like a local concept. You want to make sure some condition, like a loop invariant, will be maintained in every iteration. But now let's think about global, just about the input itself. There's got to be some input condition and also output condition. So to start with, let's look at precondition here, okay? And also the post condition, which will be asserted at the end, right? Let's look at these two only. All right, let's brainstorm a little bit, right? So precondition should be rather straightforward. So you want to think about, in order for us to be able to compute the maximum, what should be some condition on the input? Not null. I agree to some extent, yes. So A should not be equal to null programmatically, absolutely. Anything else? If you want to compute a maximum, and you want the result to be well-defined.
Well, I mean, if we want to compute like a true maximum, you need two values to compare.
Or at least one value to compare, right? So if you got one single, an array of length 1, let's say only 10. 10 is the maximum, no problem with it. But what if you have an empty array? In which case, what should be the maximum? Because presumably, any maximum you kind of extract from the array should be a member in the array. In this case, the array is empty, right?
Isn't that covered by the null statement?
Oh, be careful here. Okay, that's good. So here, if A is not equal to null, does it necessarily mean A is not empty? Oh, okay. Okay, that might be good to clarify, okay? So guys, what we are seeing here is saying that array is not null. Is it the same as saying it is not empty? Right? So conceptually, when you say A at least it's pointing to some objects, right? In that way, you can say A is not equal to null. That's what we are saying. But whatever we are pointing to here, for example, you might say, let's say integer array A would be new. Integer 0. Empty. In which case, we're still pointing to something there, just not null. In this case, A is not equal to null. And we also know that A.length is actually equal to 0. Right? So there are two different things. Right? Follow? All right? That's important, programmatically to know. All right? So now we want to somehow say maximum, yeah, go ahead first.
I thought this filled it with like the default value, which was
0? Well, okay, thinking this way. Whenever you're creating an array, of course, you gotta fill out the value to every slot that's available to you. But in case this value here is 0, in that case, there's no valid index in the array. It's as if you just got empty collection, empty set, really. In which case, you have no default value to fill out because there's no slot for you. Right? You see what I mean? Yeah? All right? All right? Any suggestion now after this long discussion, right? Of course, A should not be null, so at least we should be able to iterate through it. But now, we want to also make sure the maximum value can be defined. Right? Greater than 0? Yeah, absolutely. Good. All right? Not empty. All right? So these two are actually both important. Okay? I'll just say conjunction, right? You can say 2. Okay, so there'll be another one. You can say A.length larger than 0. Or you can say not equal to 0. That's equally good because it cannot be negative. We know that, right? You can either say not equal to 0 or larger than 0 or not equal to. Okay, that's fine too. All right, let's now figure out the fun bit, right? This one, the post condition. Okay, the post condition here basically is more like a condition. Okay, let's talk about what post condition in general really is. Okay, post condition here, post condition. It is, in general, supposed to relate between the input and output, really. And you may actually refer to some local variable if necessary. Okay? It's more like a relation between input and output. Okay? That's the very simple definition, but it's powerful enough. Relation between the input and the output. So input here is A. That's the input. Eventually, we want to return the result. So this is the output. So we are basically asking, for example, what's the relation between output here and the input here? Let's say given particular input array right here, we know that the result should be 40. Okay, so now we know the input and we know the output. How do we express a relation between them? And you can get a help from, maybe some help from, well, normally when you specify post condition, you shouldn't really need a help from local variable. I think input and output should be good enough. But when you refer to loop invariance, you may have to refer to local variable. I'll put it down first. Okay, and I'll take Josh's input. Okay, so when we talk about R, the post condition. Okay, versus when we talk about loop invariance, Li, loop invariance. Typically, this one here should definitely mention the input and also the output. And you shouldn't need to mention local variables. Because conceptually, those local variables are just for intermediate results computation. At some point, all those final values should be reflected in the output anyway. So you should only talk about input and output. Okay? But for the loop invariance, it's a little bit different. It's more like a showing the progression, of the computation for these variables. So it definitely should show the input, also the output, and also you may have to need a loop counter, very typical, and also other local variables if needed. Okay, it's a very general guidance, right? So whenever I can ask you to specify post-condition, of course, you will have to just only specify relation between input and output. For looping variance, you got more help. Oh, how about here? Precondition, let's be complete. And for precondition, simple. You only refer to the input. You don't have to worry about the output, right? Just for the precondition, right? All right, so any idea about how we can specify the relation between this result here and here? You can even think about informally is okay. We'll try to formulate it together. Josh, go ahead first.
Result is greater or equal to all values of A.
That's pretty good first approximation. Yeah, I agree with you. Anyone else who would like to say something? I think Josh's answer is pretty spot on already. We just need to formulate it. I'm pretty sure everybody will agree. Okay? So what Josh said, which I would like to write down as well, is always good for you to think about something informal and then express that, in terms of logic. Okay. So here, the post-condition here will be the result is, would you say strictly large than or larger than or equal to?
Larger than or equal to, it's going to have one value where it's equal.
Yeah, exactly. Because result got to be correspond to one of the values there, right? So you cannot say strictly larger than. Okay. So result should be larger than or equal to each value in the input array A. All right. I think that's pretty good. Right. For example, in this case, we got 40 larger than or equal to this, 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 and this. Right. They all hold. So what we want to do is because we don't know how long the array is, you cannot just write this down individually. For this particular one, you can simply say maybe result larger than or equal to A0 and result larger than or equal to A1 all the way to result larger than or equal to A3. Right? That one is more like a naive, first approximation. But the problem is there's no guarantee that you always got an array of length 4, not necessarily. So now we want to formulate it, right? And you do have some help from logic. Since we say it's more like a property that should be universally true for every element. So is there any operator we can use from logic? I kind of gave you one hint already, universally true. Universal quantification, right? Okay, good. Okay, let's now write it down. Okay. So now, let me just put this aside, right? I'm gonna don't have any more space. Okay, post-condition. Okay. And let's also take this informal idea. Okay. So this will be something you also got to get used to, right? In the test or the exam, you might be asked something like this, okay? Okay, so let's start with universal quantification. It's a universal property. So now for every, okay, we want to say for every element in the array, they should be less than or equal to the result. We can say result larger than or equal to that. Doesn't matter, right? They're symmetric. All right, so now how do we say every element in the array? Because the array is not a set, you somehow have to use the indices, right? In this case, index can be 0, 1, 2, or 3. So let's use a variable, okay? And here, I would suggest we don't really use I, because we already got I right here as a local variable, so you don't want to have any clash, okay? Let's use j. I can say for every j, and let's specify the range of j. Now, what should be the range of j? Help me out. 0, okay, less than or equal to j. Less than or equal to? A dot length minus 1, right? Of course, you got choices. You can, I personally prefer less than or equal to on both ends, but if you like, okay, I'll show you choices, right? A dot length minus 1, or if you like, you can also write, which is logically equivalent, less than A dot length. That's also fine, okay? All right, that's good. And then we only consider those values of j that's in this range. Other than that, we don't really care about other values. So that's why we're going to have an implication, right? Okay. If for those j value that's within this range, we consider the following. Now, what should we put on the other end? Right? We're going to say that A at index j, right? Then think about the j we're referring to, j here, and j here. Aj should be less than or equal to result. Of course, alternatively, you can also say result larger than or equal to Aj. I think that maybe this one might be slightly more explicit since we're talking about maximum, right? So, doesn't matter. Both are correct, all right? So this one here is a post-condition, just kind of revisiting the predicate logic, just how to use universal quantification. And you have to make sure you always specify the range over here, and you only worry about that particular range. Okay, let me just put some notes as well. So this one here is saying, if the j value is within this range, then we consider this condition. Then this condition should be true. Right? That's really from your 1090 or 1019, right? Discrete math. All right, any question about the post condition, right? That's it. All right, so precondition here and post condition right here. All right, good. So that's the first part, right? That's basically the first exercise, right? We're going to walk it through, and now we want to think about loop invariance. Okay. So this post condition here actually is very nice because conceptually we are saying that the result over here is such that it's going to be applicable to the entire range of the array, such that result can cover really every element in the array. So result is larger than or equal to none. Good. But the way the algorithm works is somehow it's going to do a linear scan from left to right. So maybe after the first iteration, we know that the result may not be the maximum for the entire array, but we know that it's guaranteed the result must be at least a subarray starting from index 0 to index 0. After the second iteration, we know that the result value may not be the maximum for the entire array, but it must be the maximum as far as this subarray is concerned, from index 0 to index 1. Right? And then we're growing that range, about the applicable range for the result. Can I follow? All right? Which means we are not really considering about this A dot length minus 1, which is going to cover all the way to the end, right here. Instead, we can change this one here to be some variable, which tells us what's the current progress for our loop. All right? That's one way to think about the loop invariance. Okay? So let me write it down. So this one here, you can think about this particular end here, the upper bound. So this one here is really the largest index. Or you can think about it's the rightmost. To derive the loop invariance, we may not be so ambitious about the rightmost index right away. We may just use some other measure to talk about what what can the result be maximum of? Certain part of the array. Result may only be applicable as the maximum of some part, or you can say prefix of the array A. So what I meant was, result after the first iteration can be considered as the maximum for just this array. After the second iteration, result should be the maximum for this subarray. After the third iteration, it should be the maximum of this array. After the fourth iteration, it should be the maximum for the entire array. So we are really somehow changing the upper bound here, right? Follow so far? Okay. Now, let's consider one potential looping variance. Okay. So we already figured out the precondition and postcondition. So let's now talk about looping variance. We're going to make sure it will be established, and also it should be maintained right here. Okay. Let me propose something. All right. That's along what I just said over there. So, or actually I can let you guys maybe think just for 1 minute. It's okay to be completely blank at this stage because it's something new to me, to you maybe. Proposed looping variance. So guys, given what I have just said, right, about this, can you suggest maybe a looping variance? Somehow it's going to be very much like the postcondition, except we cannot say this right here. We're going to say something else that's going to tell us where we are for the current iteration. I'll pause for 1 minute. You can think about, right? I'm basically telling you this postcondition can almost be copied verbatim for our looping variance, except maybe the upper bound here cannot be this, because that one is already at the end of the array, which we cannot achieve right away. We have to go bit by bit, iteration by iteration. Any idea? Imagine that if now it's the test or exam scenario. In that case, you know that your looping variance must be very much like the ultimate postcondition. But now you just have to adjust certain parts of the predicate. In that case, your safest bet is to go back to the algorithm and see if there's any local variable we can use, right? We talk about local variable kind of tell us where we are in the intermediate calculation. Less than I or less than or equal to I?
Because, if I'm looking at the first part, like line 5, less than or equal to I would work, but if you look at it, because I equals to I plus 1, and at one point I plus 1 would multiply all length, so it won't work anymore.
Okay, pretty good. You know, I kind of like your explanation. You're definitely getting between the two exercises I want to do, yeah. Okay? But at least we kind of agree that we have to maybe use the I value, because I value tells us where we are, right? But somehow we just have to, we're not exactly sure whether we should just replace this part here by I, or possibly I minus 1, right? That's really what we are not exactly agreeing, okay? All right, so again, so what you want to remember is if you really believe that the looping variance should be just like the postcondition, what you're going to change will be certain part, it should be replaced by some local variable, for example, the loop counter, right? That's a general principle you want to remember, okay? So your fellow students said very correctly, we have to use I. I also agree. That's the only local variable we have, right? You have nothing else. Okay, good. Okay, let's use that. All right, let me do the simple one. Why don't we say we just replace this guy here just by I, let's say. Let's see what happens, right? Very good. Okay, let's do that. So the proposed looping variance goes like this. So I'm basically copying the entire postcondition here. For every j, 0 less than or equal to j, less than or equal to I. All right? Implies the result larger than or equal to aj. right? So that's what I propose, let's say. So now the question is this appropriate? All right? To really show that it is appropriate or inappropriate, you basically have to check two things. Number one, can this looping variant be established by the S init? Number two, can this looping variance be maintained between each iteration? Right? So these are the two things you got to check. Right? So the best thing to do is to draw a tracing table. I think like what we did in the lecture. Okay, let's do that right away. Okay, and of course, if we somehow decide, okay, if this turns out to be the good looping variance, in that case, we should be able to have the right final answer after 4 iterations because the array of size 4. If this cannot be the right one, so somehow you will fail, some violation at some point. But I can see exactly. Okay, let's use the same input array right here. Okay, so we're going to put 20, 10, 40, and 30. Okay, the same array, let's say. Okay, let's draw the table, and you'll see exactly. Okay, we gotta be precise. So let me have several columns here. 1, 2, 3, li. Okay, so after certain iteration, okay, it dot iteration. And then the value of the loop counter I, and also the value for the output variable result, and also whether or not the looping variant is true. And also we got the condition B, right? So basically this condition here is B, the state condition, right? We're just using the same notion as we did in the lecture, okay? Condition B. Okay, let's now trace. So the first one there will be initialization. You can think about S init, okay, which we said is, this is S init right here. Okay, so this is S init. After that, I will be 0, and the result will be A at index 0, which will be 20. Okay? And now let's do a quick check, right? How do you check this? So here, looping variant here, this will be just 0. So J is now between 0 and 0. Only one value, just 0. So now result, which is 20, larger than or equal to A at index 0. True. Everybody convinced? Established. All right? True. Right? You can also say, this tells us it is established. And after this, I, which is 0, is not the same as a.length, which is 4. True. So that means let's go for iteration. Okay? So I can also say a.length over here, of course, for the example we are doing, is simply just 4. Okay? Okay, so looping variant for this one here, established. And let's now see how far we can go to. If that's the appropriate looping variance, we should be able to go until the end. But let's see. All right. And let's now go for the first iteration. After the first iteration, we know that I will be incremented from 0. Oh, sorry. Did I say? Oh, yeah. So from 0 to 1. Beg your pardon. Okay. So that'll be from 0 to 1. And what will be the result for the first iteration? You're basically just comparing A at index 0 with the result, which is 20 itself. So that means you shouldn't really update it. Result will stay to be 20, right? So you don't really execute this, okay? So result will remain to be 20. Of course, if you want, you can also give it a try. So rather than starting from maybe 0, you can start from 1. And then here you can just say 0. That's also possible, right? It's a different way of implementing the algorithm, but you can definitely try. Okay? So after the very first iteration, we know that we have already covered 0 here. Okay? It's done. So now if you evaluate the looping variance, what should we do? Okay? So now let me write it down here. So this will be star. To evaluate it, it's going to be for every j, 0 less than or equal to j less than or equal to. So now, remember the looping variant is checked after I is incremented. So now the value here should be 1, right? Should be 1 here. And then result should be larger than or equal to A, J. Is this true? It is, right? Okay, let's see. So here, J value should be 0 and 1. So 0 and 1, 20 and 10. And the result so far is larger than or equal to each one of them. So we are good as far as the first iteration is concerned. So this will be fine. Okay? And then the I value is now 1. 1 is not equal to 4. So go for another iteration. All right, good? Now, guys, why don't you take 2 minutes or maybe 1 minute only? How do you think in the second iteration we actually satisfy looping variance? Critical. So what you want to do is think about what's going to happen in the second iteration, where we're going to look at I value being equal to 1. At the end, it's going to be incremented from 1 to 2, right? Okay, I'll pause for 1 minute for you guys to give it a try. Josh, are you lost or you're kind of following? Following, good. You got to be very careful about which I value you're using, right? Let me just say it again, okay, very quickly. So when you actually compute the result right here for the current iteration, you're basically using the I value before the increments. In this case, it would be just 1. However, when you evaluate the looping variance, it's really at the very last line, which means I has been incremented from 1 to 2 already, right? That's a very critical hint for you. Just remember, looping variance always evaluated at the end, after all the updates. Okay. Okay. Anybody can at least tell me a definite answer from your end? You think looping variance maintained or violated?
Yes.
Maintained?
Yes.
You mean yes violated or yes it's maintained? You gotta be. Which one? Maintain or violated? You think violated, okay? You think so as well? Okay, good. Okay, that's really going along your intuition. That's really good. Okay, yeah. Okay, let's see. It's violated. Okay, so we know that at the end of the iteration, I is going to be incremented from 1 to 2, right? Let's put the 2 down first, okay? And then, what's going to be the result? Basically, from the previous iteration, result is 20. But now we are looking at 1 over here, index 1, which is 10. 10 is not larger than 20, right, according to this. So we don't really update the result. Results stay as 20, all right? All good. And now, when we evaluate the looping variance, okay, let me write it down side by side, okay? When I evaluate the looping variance, the I value here is actually equal to 2. From the previous one, the I value that we evaluate will be 1. Okay? So now we're going to say for every, so okay, I'll put it here. Star. For every j, 0 less than or equal to j, less than or equal to 2, right? And then result larger than or equal to aj. So now we got to consider 0, 1, and 2. All right? So now if we consider that, let's see. The result right now is remain to be 20. 20 larger than or equal to 20, good. 20 larger than or equal to 10, fine. But now 2 is really supposed to be the one we look at in the next iteration. We are already considering it. So now 20 larger than or equal to 40, false. Violation. All right? So this one here is not good. Okay, I'll also write down the reason for you. Okay, so this one here is no good. Okay, loop invariance violation, because the result larger than or equal to A2 is false. Okay, in this case, the result remains to be 20. And A2 is actually 40, which we haven't got to just yet. That's going to be done in the next iteration. Right? It's a looping variant violation. Right? So everything else is not important anymore. Right? So this looping variant here is not appropriate. Inappropriate. Because it cannot be shown as maintainable. So for this course, I think beyond this course, right? So there is certain literature just about, you can actually argue about the looping variant being preserved and also maintained logically just on the paper. But I think that we don't need to go that far. In this course, whenever you're considering certain looping variants, you will just have to do this tracing approach. I think it's more intuitive for us, all right? So now, this is not good. How do we fix it? I think what your fellow students suggested before, can you say that again? How should we fix it? I minus 1, we can say less than I, right? Good. Okay, awesome. Okay, so let's use the same table here. So for this part here, I'm going to suggest the fixed version, and then exercise for you is to finish the tracing table, and then I'll give you some notes afterwards, okay, for you to compare. Okay, right here. So now the fixed looping variance will be here. That's the final one. So the fixed looping variance will be for every j, okay, 0 less than or equal to j. You can either say strictly less than I, okay, implies A, okay, that's the result, larger than or equal to A, j. Alternatively, this part here, you can also say less than or equal to I minus 1. Okay, you can go either way. Okay, and your exercise is to show that this looping variant is appropriate. Okay, so exercise. Show this looping variance is appropriate. Number 1, it is established. Number 2, it is maintained. And you can use a tracing table. Okay, trace table to do it. All right, that's good. I'll leave that exercise for you. So when I post the notes, I'll give you another annotation version on my notes, so you can also compare. All right. Okay, final bit. Let's say we skip the break. I'll do another one, just a few minutes, and then we're done for today. Okay, you can ask me questions later if you want to. The final bit is to say, given our precondition, postcondition, and also the looping variance, so now what we want to do is we want to finally show this algorithm is actually correct, right? That's what we want to do. So if you remember the condition we set earlier in the lecture, anybody recall? How do we relate the, okay, let me highlight the condition you should really refer to. We got this condition here, which we call B, right? And also we got our looping variance right here, and also right here. And also we got our postcondition as well, right here, okay? In this case, we also have our precondition, okay? Precondition sometimes can be useful as well. How do we relate them, right? There should be a formal relation we have to somehow show, all right? Anybody remember what that should be in general from lecture? June, do you remember? Do you remember? No. Okay, sure. Let's not do it right here. I'll remind you. So here, so what we said in the class was, given that we already exit from the loop. That means the B condition here is not true anymore, right? And also given that the loop invariance has been maintained from the last iteration, right? So this one means we exit from the loop. And this loop invariant here is really maintained from the last iteration. In the last iteration, okay? And given that, we should have until the post condition, basically, all right? That's what we have. Yeah, the precondition here in some way is not very useful in this case because this is already the last iteration, and this precondition is only true at the very beginning of the loop. So it may have already been falsified sometimes, right? So you don't have to include the precondition. That's my point. Okay, only this one here, right? There's a very important relation for you to remember. Okay, right here. Right. So let's now try to write down this case. Right. Let's do it together. Right. So since you haven't seen many examples so far. Okay. So I don't need this anymore. Okay, let's just put it here. Okay, that's a general connection. Okay, of course, this one here is our post condition. Let's try. So what we have is, first of all, let's start with the not the case, we're staying in the loop. So I not equal to a dot length. Okay. And we know that the loop invariance is the case for every j, 0 less than or equal to j, let's say, less than I, okay? Implies result should be larger than or equal to a j, right? This one here is the B right here. And this is a condition that we check for establishment and maintenance in the previous 2 pages. And these two should entail the post condition, which we also did at the first page. For every j, 0 less than or equal to j, less than a dot length, implies result larger than or equal to aj. All right? Okay, pause for a moment. Number one, convince yourself every part is something we said already, right? Just make sure I didn't copy anything wrong. Number one. Number two, do you think this implication is true, trivially, somehow? That's the second question, right? Anybody would like to give a try to see why we can say this implication is trivial, trivially true? If you recall back in 1090, or maybe your previous math course, there's one proof method called assuming the antecedents. Have you heard about it before? Huh? Oh, you forgot. Okay, maybe it's a long while ago. That's okay. I wouldn't blame you for that. That's okay. So whenever you want to prove an implication here, one proof method is called assuming the antecedents. Okay, assuming the antecedents. Yeah, that's a proof method. Okay, so so we know that this is antecedents and this is a consequence, right? Implication terminology, right? In order to really prove that this implication is true, I can assume the blue part, which is the antecedents, and use whatever I have over there and show that this is the case. Josh, you got something?
Can't we just assume that if it's I equals a dot length, that I equals a dot length, and we can just sub it in?
Yeah, that's exactly right. But gotta be, yeah, exactly, right? So when we say assuming the antecedents, we basically assume here and we assume here. And once we have done the substitution, we got exactly this. Right? Okay, let's do it. Okay, let's be careful. Okay, so you can say this is antecedents number 1. Okay, this is antecedents number 2. So we assume A1, A2. Okay, in that case, we know that from A1, now you can see the advantage of writing the condition here this way, because somehow we made it very straightforward in terms of its negation, right? What's the negation of not equal to? Well, equal to, right? From that, we know that I is exactly equal to A dot length at the end of the iteration. Exactly. It's like a largest index plus 1, right? After the plus 1, the last iteration. And then, so from A1, okay? And then we can substitute, okay? So think about number 1, number 2, number 3, substitute I by A dot length in A2. Okay, so basically we are substituting the I here. There's only one occurrence of I right here, substituted by A dot length. And we got exactly the consequence we want to prove. Exactly. All right. So that one would be this gives us the consequence to prove. Okay, sorry, a little bit messy here, but I'll read it to you. So you substitute I by A dot length, because we know from A1, I will be just the length of A. And then once you have done the substitution over here by A dot length, this guy here is exactly identical to this one here. That's what we got, all right? Okay. So this will give us the consequence that we want to prove, right? That's how we show, okay? Of course, this one somehow is only a tutorial example, so I somehow made this one rather simple and straightforward. I think that you have to follow a similar pattern. In the test work exam, if somehow, even after the substitution, it may not be exactly the same, you have to do some additional arguments. So that will rely on your logical reasoning skill, okay? But I think that this one gives you a very good big picture about what you should really do. All right, let me do a recap, and then we're done, okay? So today we kind of did a very complete workflow about the looping variance, okay? So we started with this particular iterative algorithm using a while loop. So we start by specifying the input constraint and also the relationship between the input and output, and also known as the post condition. That's what we start with. And in this particular case, we consider the post condition here, especially the upper bound for the loop counter. So this one here can somehow be made a little bit more specific to the loop counter that kind of show that we want this progression of the loop to be reflected in the actual post condition. That will make the looping variance to be specified, right? And then that's what we got as a looping variant. This is the first proposal. And if you're given some arbitrary proposal for looping variance, you ought to judge by checking that for establishment before the very first iteration, and also maintenance between the at the end of each iteration by using a table.
Sorry, I got a question.
Yeah, go ahead.
I'm so confused why the looping variance is not maintained in the second interval or the third iteration.
So yeah, so it's not maintained at the end of the second iteration. It's not maintained.
But it is because
It is not, because tell you why. Would you agree after the second iteration, the result remained to be 20?
I thought it's like the if statement's already been invalidated, right? So now the result is already 40.
No, it wouldn't be, because in the second iteration, index will be 1. Because we start with the index 0, right? So for the first iteration, we are only looking at this index. In the second iteration, we are only looking at this index. You see what I mean?
Except the third iteration of the second.
No. Look at the code, right? So here, we start with I to be 0. Agree?
Yeah.
Okay? So in the first iteration, we are only looking at 0 index. And then we increment I by 1 at the end of the first iteration. So in the second iteration, we look at when I is 1. In that case, the result is not going to be replaced by 10. It still remain to be 20. It will only be updated to 40 in the third iteration. But by then, the looping variant violation already occurred.
Because you assess loop variant after you.
Yes, so that's the definition for looping variant. Yes, that's really the essence for this looping variant here. So you only check the looping variance after everything has been done for that particular iteration, including I being incremented for the next iteration.
I think the if statement's already been invalidated, so now your result should be 40. Before you validate your.
Okay, in the second iteration, do you agree? I value is 1.
Yeah.
Agree? So when you get to here for the second iteration, AI is 10.
Yes.
In which case, 10 larger than the result, 20 is false.
Yes.
So you don't really update it. So result remains to be 20.
Yeah.
And then you increment I from 1 to 2.
Yeah.
But result is still 20. And then you check the looping variance. Why don't you maybe come to me, that's okay, or just watch that part of when I explain the trace table. It's very important, right? Okay, then maybe we can go over it again. Okay, Josh, go ahead.
Did we end up deciding what the actual LI was supposed to be?
The actual looping variance?
Variant?
Yeah, so this one is, this one here, you can see the condition there for the upper bound is actually not right. Because this one here, less than or equal to, is not right. So it's going to cause some looping variant violation right here. So this one will be correct, and that'll be exercise for you to verify.
Well, that was more my question, because I was thinking.
Well, so what's your question?
Doesn't this break because our initial LI assert will fail because you can't have a value of j that is equal to 0 but also less than 0?
No. So when you first check this one here, I will be just 0. Okay, so let me do it again. This is a looping variant, right?
Well, because it's 0 less than or equal to j less than I. But if I is 0, then j has to be a value that's greater than or equal to 0.
Okay, so, you're talking about this point, right?
Yeah.
Okay, so at this point, we agree that I will be 0. Okay, so now, j is between 0 and 0 inclusively. J value can only be 0.
But
The fixed version.
there's a fixed version is not less.
Oh, no, okay, let's talk about this version here, right? Oh, I know where you want to go to.
That's what I was asking.
Okay, so are you asking about this version here or the fixed version? Fixed version, okay, good. I want to be sure, okay? You're asking about, in the fixed version, why this will be established, right?
Yeah.
Okay, good. Okay, I'm glad you asked. Okay, I don't mind talking about this one specifically. Okay. Okay. Right here. And we talk about this one here, right?
Yeah.
Okay, good. I know exactly what you might be wondering. For every j, 0 less than or equal to j, less than what value? 0. Okay, good. So far, so good. Implies result larger than or equal to a j. Guys, are you following? Right? Well, I'm just doing replacement for the fixed looping variant. So now the question is, what should this evaluate to?
Or is it just we don't evaluate it because there isn't j?
It's going to evaluate to something. It's going to evaluate to either true or false, basically. All right? So now the question is, this particular predicate here, is it going to evaluate to true or false? That's the main thing. And this does require your knowledge from the logic course.
Okay, it is going to evaluate the true because it's
How come? Why would it evaluate to true?
the implication of the first part is false, so it doesn't matter.
All right. How about just this part here? We know that j is a number. Is there any number that can be larger than or equal to 0, but also less than 0 at the same time? Is it possible? No. So this part here basically can be simplified into false. And then from your logic course, when you say false implies P, any predicate there, proposition, it'll be equivalent to true. All right? I'm glad you kind of asked because I did want to mention that at some point. Now is the point. So that's why this looping variant here is true trivially, just because you have no value to even evaluate, just like a false. So empty range will be just true automatically. All right? That's really your question, right? Good. Okay, awesome. Yeah. Question?
What is D in this scenario?
Huh?
What's D in this scenario?
D? What do you mean D?
Like 0 less than greater than J less than greater
both
than
0.
Oh, they're both 0? I'm just lying.
D? Oh, no, sorry, there's no D, right? Yeah, yeah, that's okay. 0, yeah. Oh, that's my fault. I should have written that better, right? Okay. All right, guys, question. Okay? Yeah, think about this example here. There are many things you can see from here. Simple enough, but you can pick up so many details. And do this exercise, please. Okay, make sure you can do it. And in the test or exam, I can ask you something along this line from here. All right, just make sure go through. And then Monday, we're going to finish the last bit about Dijkstra, and then we cover something a little bit new. And then we'll talk. Okay, thank you so much. And then I'll see you next week.